There we go. Okay. So does anybody know what a polynomial is? I know that this is a Math 13, 14. This is college algebra. It's the standalone. So there's some sort of presumption on my end that we have heard of polynomials before. Maybe we're a little bit rusty or fuzzy on what the definition is. But can anybody take a crack at what they think a polynomial is? Or is it something that you've heard before?
I've heard of it before, but like you said, I'm a little rusty on it.
Yeah. So I'll go ahead and give you guys the definition for it here. Let me go ahead and share my document camera. Wait up. Oh, that's right. That's why that's happening. Give me just 1 second. Stop sharing. Okay. Now we can share from the second camera, I think. Yeah. No. Switch camera. There we go. Okay. Can you guys see this okay? Do I need to make it a little bit more sharp? Let's see.
It's good. Okay.
So the first thing that I want to talk about is what is a polynomial, right? Because we might be rusty. It might have been a while for some of us back in high school days when we heard about polynomials. A polynomial expression, or just simply a polynomial, is a kind of an expression that we're going to come across a lot in mathematics. And it's an algebraic expression that combines numbers, variables, and arithmetic operations. So what do I mean by arithmetic operations? I simply mean that the operations that you learn in grade school, addition, subtraction, multiplication, and division, they're going to sort of glue our variable terms and our numeric terms together into a long string of terms that might be added or subtracted to each other. So just a little bit more vocabulary here. What is a term? Terms, well, really it's what we call things that are separated. Let's call them objects, and they're separated by addition or subtraction. And maybe before we really start getting into these definitions, we have an example of a polynomial. So one kind of polynomial would be like a quadratic trinomial, 3x squared plus 2x plus 5. So we have a polynomial expression here. Each of the terms is separated by the addition symbol. So if you were trying to count how many terms are in this expression, there are 3 terms. I have this term here, and this term here. Again, separated by the addition symbol. Some more vocabulary. Well, we're going to be talking about variables a lot. And for those of you who are rusty or think that variables are a scary thing, a variable is just a placeholder. It's an unknown value. So if I went to the supermarket and I didn't know how much apples cost, I could still pick up 3 apples. Even though I don't know what the total cost is going to be, I know that I have a quantity of 3 apples, right? But I don't know the cost of the apples. So I could say that apple is going to be my placeholder for whatever the actual monetary cost of the apples will be, or what I'm going to have to pay at the counter. So I like to think about a placeholder here. And then if you are given a value for the variable, well, then you can insert that value and then sort of solve or simplify the expression. Okay, so here among these terms, we have 2 different kinds of terms. We have variable terms, anything that has an X or a letter, that is going to be a variable term. So we have two variable terms here. And then we have something that's just a plain number. And in mathematics, we call those constants. And the reason why we call them constants is because, okay, going back to my supermarket example, if I went to HEB, an apple might cost 98 cents. But if I go to Walmart, yeah, it might be 68 cents for an apple, right? So depending on which store I go to, the value of the variable could change, right? So it's problem dependent, it's situation dependent. But the constant, this $5, let's say that we live in some sort of feudal society where the income tax, I'm sorry, the sales tax is just some flat $5 fee. Like you must spend at least $5 in order to use your credit card, for instance. Well, then we know how much we're going to be spending. It's 5. It's a known value. It's not going to change from store to store, assuming that the local laws fix this number, right? Whereas the price of the apple might depend on the situation or depend on the store that we go to. So a fixed value is what we call a constant. In the polynomial, the leading term is the variable term that has the highest exponent. So in this case, I've written the polynomial such that the highest exponent term is in the very front on the left-hand side of the expression, 3x squared. So this term, 3x squared, has to be the leading term. And then overall, we can say that the degree of the polynomial is the highest exponent on a variable term. Okay, so I'll give you guys a second to write that down. So can anybody tell me what the degree of this polynomial example is?
Two.
Yeah, this is a second degree polynomial. It's degree 2. Okay. So that's basically the structure of these objects that we're going to work with called polynomials that combine numbers, variables, and arithmetic operations. We're going to see this time and time again. And we're going to need to be able to manipulate them in the same way that we manipulate numeric expressions, that is expressions that have numbers only, right? Like if I told you what is 5 plus 2, that would be an expression that's purely numerical. And you could simplify that expression because rather than saying, you know, I'm going to go buy 5 plus 2 apples, it would be simpler for you to say, I'm going to buy 7 apples. So we're going to, just like we can manipulate numbers, we can sort of simplify expressions that have numbers, or we can even break up numbers. Like if I said that I owed you $10, I could break up $10 into ones, but 10 of them, right? 1 times 10. Or I could break that down into 2 $5 bills, 2 times 5, right? We can break up and manipulate numbers, and we're going to have to learn how to do that same sort of thing with these algebraic expressions, even though they have variables in them, okay? So because we're going to learn how to break up these variable expressions like this, or these polynomial expressions, we need to know something about how they're made. So the first thing I want to talk about is multiplying polynomials together, okay? So let's start by multiplying out some polynomials. And here I'm sort of going to draw upon your previous knowledge of multiplying polynomials. So if you make a mistake, this is the place to do it. Don't feel bad. We are going to figure out where our lapses in judgment are, so to speak, and then sort of correct those things so that we can, you know, do the correct process moving forward. So for this first example, I want to just multiply monomials, that is polynomial expressions that just have one term. So if I had for example, 2x, and I wanted to multiply that by 10x, does anybody know what the result of this multiplication would be?
20x. I know.
20x squared.
Yeah. Wait, no. Yes, 20x squared.
Okay,
Wait, no, just
Yeah.
20x. I think it's just 20x.
so we have some 20x, some 20x squared, right? Okay,
I'll take on the 20x squared.
yeah,
Isn't
Yeah.
this where Punnett squares come into play?
they will when we start getting more polynomials together, like with more terms. We don't call them Punnett squares here, but it's the same process. Punnett square is a concept from biology. But yeah, so we're hearing some people say that we need to have 20x. Some people are saying 20x to the second power, 20x squared. And there's always some confusion here among students about what we do with the x's. Because it's pretty clear that everybody knows we need to multiply the 2 and the 10 together. So to sort of elaborate this problem and sort of break it down into excruciating detail, we need to know something about multiplication in general. And that is, there's this property of multiplication that says multiplication is commutative. What does that mean? It means that I can change the order of multiplying the terms, and it doesn't matter what order I multiply the terms in, I will get the same result. So order doesn't matter when we multiply. 2 times 3 is 6, and 6 times 3, I'm sorry, 2 times 3 is 6, and 3 times 2 is 6. So if you reverse that, those numbers, the order, you still get the same result. That is not actually true for other kinds of mathematical objects, but it is true for numbers, and it is true for polynomials. So if I wanted to rearrange this, I could put 10x times 2x and I should get the same result. But also, if we look at each of these terms that we're multiplying together, the term right here in front that's being multiplied by the variable is called a coefficient. I'm not sure if I wrote that definition down or if I just sort of glossed over that. So really, this number that's next to the variable is being multiplied by the variable. So this is sort of like a placeholder. Let's say that I have 2 apples. Then the total cost of the 2 apples would be 2 times the number of apples I have. Or the cost of the apples. And I don't know what the cost of the apples is, but that doesn't matter. It's implied here that 2x is 2 times x. And the coefficient on this variable term is 10. So again, it's implied here that even though I don't have a little dot or a little multiplication symbol in between these two things, it's implied that we're multiplying 10 times x. What that means is that this expression can be rearranged such that we write it as 2 times 10 times x times x. We know that 2 times 10 simplifies to 20, and everybody was able to get that pretty clearly. But then can anybody tell me how we could simplify x times x? Is x times itself still just x?
No, they were right. It's x squared.
Yeah, it's x squared. In the same way that if I had 2 times itself, I could write that with an exponent as 2 squared. Or if I had 3 times itself, I could write that as 3 squared, and so on. Does that make sense?
Yes.
So you have to be very careful when you're multiplying polynomials because students will sort of mess up the multiplication of the variables. So when you multiply the variables, it's like you are adding their exponents together. You're counting up how many x's you have in total, and then that will be the exponent. Okay. So let's look at this example and see if we can solve this together. We have 4x squared, and we want to multiply that times 3x to the 3rd power. Can anybody tell me what the result of this should be?
12x to the fifth
to
power.
the fifth.
12x to the fifth power. Does anybody have any other ideas?
Don't we? I don't know.
Any other suggestions? Are we 100% confident that it should be 12x to the fifth power?
Is that or 12x to the sixth power? You might multiply the 2 and the 3 on the x, but I'm not sure.
Well, let's think about this previous problem that we did. If we have just a variable by itself, and we're multiplying them, we just have x here, for instance, we could say that this is x to the 1 power. We just never showed the first power. And this is x to the first power. So if we had multiplied these together, and if we had multiplied the exponents, then what is 1 times 1?
x1. It would still be 1.
It would still be 1. So it looks like what we're really doing here is adding up those exponents, right?
Okay.
And I was just trying to put some doubt in your mind, because you're never going to feel 100% confident in what you're doing until you get a lot of practice. Even then, it's not going to feel like 100% confidence. But I just wanted to put a little bit of doubt in your heart for a second. You guys were exactly right. This should be 12x to the fifth power. Okay. And to belabor the point a bit, you could, if you wanted to like really get in there and understand it, rearrange this multiplication. Again, this is 4 times x squared, or you could put 4 times x, right? And this one is 3 times x to the third power, or 3 times x times x times x. So if we wanted to rearrange it, we could write this as 4 times 3, put the numbers together, and then times x, that's our x squared. And then 3 more x's, and we're multiplying all of this together. So I'm just going to throw dots in between. And we can simplify this, right? 4 times 3 is really easy to simplify. That's 12. And then something times itself 1, 2, 3, 4, 5 times tells us that we should have an exponent of 5.
Fair enough.
Yeah. Now you're not going to want to do that for every case, because if these exponents were like 4x to the 35th and 3x to the 74th, you wouldn't want to write x that many times out. You'll just have to remember that you're adding up the exponents. Okay, let's look at another expression. Another set of monomials. Let's multiply 3, nobody can see this. 3 x to the 5th times -6 x to the 6th. What should I get from this multiplication?
Negative 18x to the 11th.
Negative 18 x to the 11th. Yeah, perfect. All right. So that's multiplying monomials, probably the simple form of multiplying polynomials. And now we're going to step it up. We're going to look at multiplying binomials and revisit our old friend that we might have heard of a long time ago called the distributive property. So let's multiply some binomials. Binomial is just a special term that we give to a polynomial that has 2 terms. So here's an example. Let's multiply x plus 3 times x plus 7. Okay. And what I mean by we're multiplying 2 polynomials here is that this first guy is a binomial, right? It's an expression that has a variable, an addition symbol, and a number. And then we have another polynomial over here. And so we need to think about it like, you know, in the same way that we would have, you know, 2 times 3 is equal to 6. We have 2 numbers here that we're multiplying. We're not multiplying numbers here necessarily, but these 2 larger objects that we're calling polynomials. So does anybody know what the process is for multiplying these 2 binomials out?
Wouldn't you FOIL them?
Yeah, but what does FOIL mean?
Do both of the problems separately and then do them together?
Well, I mean, you sort of have to do them all together. I don't know exactly what you mean by do them separately.
We can put
Oh.
these ones in the square.
Isn't it like first, opposite, inside, and last?
Close. It's first, outer, inner, last. And it's just the order in which you have to multiply the terms, right? So if this is our first polynomial, then the first term is x. And if this is the second polynomial, then the first term here is x. So we're going to multiply the first terms, and then the outer terms, and then the inner terms, and then the last terms. So it's 4 sets of multiplication. I will probably only in like when I'm lazy and tired will I say go ahead and FOIL it out. But a lot of times I will say distribute the polynomials. That's another way of describing what we're going to do. This is the situation where I think somebody in the class mentioned Punnett squares. You could use this box method to multiply out the terms. But I like to just say that we're going to do a handshaking method. Let's pretend that these guys are at a party or they're going to a party and they've never met these two people before. That means that if they need to introduce themselves, person 1 from this group needs to shake hands with each of these people. And then person 2 from this group needs to shake hands with each of these people as well. So we're going to multiply, and I like to draw arrows here, the x times the x, and then write that product down. So x times x should be x squared. Then we'll multiply x times 7. Does anybody know what x times 7 is?
7x?
Yeah, it's just 7x. Then we'll have 3 times x and 3 times 7. So we should get 2 more terms here, plus 3x and plus 21. Notice that when I multiplied 2 binomials together, I had 2 terms in each of these polynomials, 2 terms here, 2 terms here. When I multiply them out, I should get 4 terms. So as our intermediate step, we can see that we have 4 terms. But now I'm going to take us back to our supermarket analogy. Some of these terms are like terms. Let's say that the x squares, I'm going to call them apples. I'll call the x terms bananas and the constant an orange. Okay. If I went to the store and said I'm going to get 7 bananas and then 3 bananas, would it be complicated for me to tell you that I'm going to get 7 bananas and 3 bananas? Or would it be simpler to just tell you I'm going to get 10 bananas?
Simpler to say 10 bananas.
Yeah. So since these are like terms, let's just combine it. Let's simplify it and just call it what it is. Let's call it 10 bananas. So we'll leave our x squared alone plus 10 bananas plus 21. And since now we have apples, bananas, and oranges, we cannot mix the two. Like if I had 2 bananas and 3 oranges, I couldn't say that I had 5 oranges, right? So we just have to leave them separated. If that is all we can do, we've combined all of the similar or like terms, then we're done. You can stop there. We've simplified, we've multiplied the polynomials out, and then we simplified our final expression. Does that make sense?
Yes.
Okay. Okay, let's do one more. I'll give you guys about 2 minutes to solve this one, and we'll see what we get. 2x plus 5 times 3x minus 4. And when you're done multiplying this out, combining like terms, and you've simplified your final expression, you can throw your thumbs up in the thumbs up emoji in the chat, or you can throw the thumbs up using the thumbs up reaction in Zoom, just so that I get an idea of who's finished or how many among us have finished. Okay, I'm seeing some thumbs up. Yeah. So let's go ahead and just jump into this. Now, in my head, when I work these out, I usually use this handshaking method where in my head, I will go ahead and do the multiplication 2x times 3x, 2x times 4, 5 times 3x, 5 times -4. But if you can't hold those objects in your head without like making a mistake, or sort of like it's too much bandwidth for you, you can use this process that was mentioned earlier, this Punnett square, this box method, where you can draw a square. And since we have 2 terms in each of these polynomials, what we can do is draw a square with 4 boxes. It's a 2 by 2. So I'm going to take the first polynomial and put it on top. That is 2x plus 5. And I'm going to put the second polynomial over here on the side, 3x minus 4. And then we're going to run through the multiplication. So wherever these intersect, with these terms intersect, that's what I'm going to multiply out. So for this first box, I'll do 3 times 2 is 6, x times x is x squared. And then for this next box over here, it'll be 3x times 5, that'll be 15x. The intersection here should be 2x times -4, so that'll be -8x. And then finally, we should have 5 times -4, which is -20. The nice thing about this box method is that the diagonal terms tend to be our like terms. So we can just say, okay, if I have 15 apples, but I ate 8 of them, or I tossed 8 of them, then how many apples should I have left over? Well, if I combine these terms, it should be 7, right? So my final answer here should be 6x squared plus 7 apples, because that's all I have remaining, minus 20. And that is the result of our multiplying, right? That's the product of these 2 polynomials. Does anybody have any questions about that? Cool. Okay, well, we spent all that time thinking about multiplying polynomials out because a lot of times we will look at an expression and we'll need to do this process called factorization. That is, with numbers, for example, we can take a number, let's say a large number like 24, and break that up and write it as the product of 2 factors, or we're multiplying 2 numbers to get 24. So let's think about this factorization or factoring. With numbers, this is a little bit maybe simpler, or it might be a little bit more straightforward. Let's think of factors for 24. Can anybody tell me how can we write 24 such that we have 2 numbers that we're multiplying together to give us 24? What are 2 numbers that multiply to make 24?
12 times 12.
12
Or
times
12
12?
times 2, my bad.
There we go. 2 times 12, right? And again, the order here doesn't matter because we're simply multiplying. Can anybody give me another set of 2 numbers that multiply to make 24?
6 and 4.
6 and 4 work for sure. I'm going to put 4 and then 6. Another set of numbers that multiply to make 24.
8 times 3. Yeah.
Times 3. Good. Any others?
$24 times 1.
There we go. Yeah, and notice that these numbers are all whole numbers, or what we call integers. They're not fractions or decimals. There are ways to multiply decimals and fractions by each other to get a whole number. But in this case, when we're factorizing, we're strictly thinking about whole numbers here. Yeah, so when you multiply numbers together, just to give you some terminology, the numbers that you're multiplying together are called factors. So all of these are factors. And they're factors of 24. So 1, 2, 3, 4, 6, 8, 12, and 24 are factors of 24. The result of our multiplication is called the product. So with numbers, we can take a large number and break it up into its factors if we wanted to. There's another kind of factorization that's called prime factorization that I should probably mention now, where you use this process called a factor tree to take a number and break it down into all of its prime factors. That is, let's say that, we started here with 2 times 12 to multiply to make 24. If I look at these factors that I got from breaking up 24, one of these factors can be broken up further, but the other one can't, right? Like, can anybody give me 2 numbers that multiply to make 2?
1 and 2.
1 and 2, right? But we already have 2. So it doesn't really help us to say 1 times 2, right? It doesn't really break down. We would call this a prime number, because its only factors that are remaining are 1 in itself. So prime numbers only have the factors 1 and itself. Every other type of number is called a composite number. And composite numbers can be broken down further. They can be broken down further into primes. So if I'm using this prime factorization process, I'm breaking up numbers, I'm looking at their factors. If I get a prime factor, I can't break that down any further. But let me look at this other branch in the tree, 12. And can anybody give me 2 numbers that will multiply to give me 12?
2 and 6.
2 and 6. Okay, and so 2 is prime again. Can I break down 6?
2 and 3.
2 and 3. Well, we know that 2 is prime. It cannot be broken down into anything other than 1 in itself. Can 3 be broken down further?
No.
No, because it's prime. So I can circle that one and say that 24, if we wanted to, we could write down 24, and that's equal to 2 times 2 times 2 times 3. Or we could say this is 2, and we have 1, 2, 3 of these, so 2 to the 3rd power times 3. And this would be the prime factorization of 24. And so this process of factorizing or factoring is we take a number and we write it down as a multiplication problem. Now that's sort of simple enough to think about with numbers, but when we're given a polynomial expression, it might be a little bit more difficult. So let's look at, let's see. Polynomial factoring. You are given 2x plus 4. A simple polynomial expression. But we want to write this down as a multiplication problem. So we want to write this as something times something else. But how do we write this as a product? Well, one way that we can figure out how to write this as a product is by examining the terms individually and to see what their factors are. What are the things that multiply to make each of the terms? So this first term, 2x, again, I said that 2x is the same thing as 2 times x, right? So I can factor or break up 2 into 2x into 2 times x. For the second term, 4, can I break this down into a product of its factors? Or what are two numbers that multiply to make 4?
2 times 2.
2 times 2. Okay, well, if I look at these terms that we have in the polynomial, they have some common factor, right? The common factor is 2 for these two terms. So what I could do is say, since we have these common factors, that I'm going to divide out or factor out that common factor. So you could think about it like this. I have 2x plus 4. And let's say that I wanted to divide each of these by 2. So I'm going to divide each of these by 2. And don't worry, I'm writing division as a fraction. A fraction is just a division problem. So you'll have to get used to me writing division with this line underneath and the number below. Okay. So if I divide each of these by 2, then these 2's should cancel out, right? Because 2 divided by 2 is just 1. So I should just have x left over, 1x. And over here, I should have 4 divided by 2 should be 2. So somehow this term here, or this expression, is related to the original expression. The only difference is that I've divided out a 2. I've divided out a factor of 2. So if I multiply 2 back into this expression, I will get my original expression, right? So that's what we're doing here. We can say that 2 times this polynomial, which is x plus 2, will return to us our original expression of 2x plus 4, right? Because 2 times x is 2x, 2 times 2 is 4. So now I've taken a polynomial expression and written it as the product where 2 is a numeric factor, and this thing x plus 2 over here is also a factor. It's just a polynomial factor. But I've written it as a multiplication problem. So I can say that 2x plus 4 factorizes or factors into 2 times x plus 2. And this is the factored form of this expression. They're the same thing, just written differently. In the same way that I said we could use 24, or we could write it out as 2 to the third times 3. Each side of this equation is equal to each other, right? If I were to throw this part into the calculator, it would spit out 24. It's just written as a product, written as a multiplication problem. The same thing is going on here. This original polynomial is the same as this in terms of value. It just looks different. It's just written as a multiplication problem. Okay, does that make sense?
Yeah. Can I see the top of the paper really quick?
Yeah,
Okay. Thank you.
you got it. Any questions?
So far, so good, sir.
Okay. So this is going to be the process that we're gonna do. Very early on, we're going to have to be able to identify something called the greatest common factor when we look at more than 2 terms, so that we can sort of streamline the process in our heads, right? Because like I said, if this was let's say that this was 36 times x to the 54th. You wouldn't want to break down 36 into all of its prime factors and then have like 54 x's trailing and then comparing that to something that also is a large number that has a ton of variable terms multiplied in it. But for these first couple of examples, we're going to break them down so that you guys can see what's going on inside the polynomial expression's terms. And then we can figure out what our common factors are. Okay, so let's look at some examples here. So we need to completely factor. And we're going to use our first method. So method 1 is factoring out I'm going to write this as GCF, the greatest common factor. Okay. So in this first example, we have 9y to the 5th power plus y to the 2nd power. We want to factor that. So can anybody, just looking at that problem and sort of reviewing the last problem that we did, can anybody factor this just right off the bat?
9y to the 7th power.
Ooh, so be careful. Remember, what are we doing? We're not combining these terms. We can't add them because they're not like terms. This is y to the 5th. This is y to the 2nd. Apples and oranges.
Why? Can we just break down all the y's?
Yeah, let's break down all the y's or the terms into their factors, right? So using the same process that we did before, let's look at this term and this term. Can we factorize 9? What are numbers that multiply to give us 9?
3 times 3.
3 times 3. So I might write this as 3 times 3, and then I might write times y, 5 y's. And then for the second term, I might do the same thing, y squared. And what does this break down into as a product?
Y times y.
Y times y, so I could write y times y. So looking at these two terms, inspecting their factors, what factors do they have in common?
Wouldn't it be y squared?
Yeah, if you look at this, we have a y here and a y here. We have a y here and a y here. So it looks like y squared is the greatest common factor. It's the most factors that they have in common. And it's 2 of those y's. So if I take my original polynomial, 9y to the 5th plus y squared, and I divided that by this greatest common factor over here, y squared. Well, when we multiplied polynomials together, we added their exponents, right? So when we're dividing polynomials, we have to subtract their exponents. So when I divide this out, I should get 9y to the 3rd power plus, does anybody know what y squared divided by y squared is?
Y. Is it just y?
Are you saying y?
Yeah, is it just y?
I think it's just 1, right?
Or is it?
Well, yeah, I mean, let's think about that for a second. Let's think about a simple example, right? If I have a number like 25 divided by itself, what is 25 divided by 25?
That would be 1.
What is 10 divided by 10?
Also 1.
What is 135 divided by 135?
1 as well.
So anything divided by itself is 1, right?
Yes.
Yeah, no, and I wasn't, I'm not trying to put you on blast or anything, but I just want to make it very, very clear because I'm sure that your classmates are sometimes have the same confusion. Anything divided by itself, whether it's a number or a variable term, If it's divided by itself, you get 1, the number 1. So
Gotcha.
y squared divided by y squared is 1. Okay, so that means that if I take this expression and multiply that GCF back in, it'll give me my original expression. So I could rewrite this as y squared times 9y to the third plus 1. And then if you were to run through the multiplication, you would see y squared times 9y to the third would be 9y to the fifth. Y squared times 1, well, anything times 1 is itself, so it's got to be y squared. So that's how we can write this as a product, and we fully factor this polynomial. And you don't have to put a little dot in between the parentheses. The parentheses here with no symbol in between implies multiplication. Does anybody have any questions, comments, or concerns there? Okay, I'm going to give you guys a few examples of these, and I'm going to throw you into breakout rooms so that you can solve them amongst yourselves and discuss them. Okay, so let me write down some practice problems. And we're just factoring out the greatest common factor. So you might have 6x squared t plus 8. Ooh. I probably should make these t's a little bit more cursive. This is a plus x t minus 12t. Okay, that's going to be the first example. 6a squared minus 18a to the fourth. 14 x to the third, y to the third, y to the second, minus 28x squared, y to the third, plus 21x squared, y squared. Okay. So write those down. I'm going to go ahead and prepare these breakout rooms for you guys. There are about almost 20 of us, so I'm going to put 3 breakout rooms. You guys are going to be randomly sorted into them. When you write these problems down, go ahead and accept the breakout room invitation and then get to work. So the invitation has been sent out.
I'm sorry, on the first equation, that middle part where it says x or 8, is that a 8xt or an 8 times t?
This is a 8xt.
Okay, just making sure.
Yeah.
Okay.
Yeah, that is a variable. You'll notice that we don't, in algebra, we don't tend to write the multiplication symbol as the x, which is why you've seen me write it as a dot or parentheses, because it'll get confused with the variable x.
Can you slide it down so I can see the last problem a little bit? The breakout group's kind of down a little bit more. There you go. Thank you.
Okay, you got it. Hey, Joseph, are you there?
Yes, I was just writing down the question.
Okay, cool. Take your time then.
Sir, can you add me to another one?
Sure.
Thank you.
Marisa, are you there as well? So let's take a breather. And then I'm going to explain how you would factorize these expressions. I sort of threw you guys into the deep end a little bit here, but really there's no other way to really master this algebra stuff. So let me walk you guys through it. And maybe some of you guys were on the right track. Maybe some of you guys made some mistakes. That's fine. That's what we're here to do. But we got to get this practice. So our first expression was 6x squared times t plus 8xt minus 12t. And like I told a couple of you, the breakout groups, what we need to do here is look at these guys term by term, look at the polynomial term by term, and factorize those terms. So we should have 2 times 3 times x times t for this first term. We should have 2 times 2 times 2xt for the second term. And then 2 times 2 times 3 times t for the third term. If I compare all of the terms, their greatest common factor was 2t. Because this one has a 2 and a t, this one has a 2 and a t, this one has a 2 and a t. Okay. So what you'll do is we'll write, excuse me, we'll write the greatest common factor down. So this is our GCF. And then what I like to do is just open up some parentheses, and we're going to write what we have left over in that parentheses. So if you notice, the original term had a plus sign and a minus sign here, separating our 3 terms. Well, I should have 3 terms in this parentheses. And whatever is remaining here, you can think about this like I factored out the GCF. So if I factored out the GCF from the first term, all I have is 3x squared left over. From the second term, I factored out 2t, leaving me with 2 times 2 times x, which is 4x. And if I factor out the 2t over here, I have 2 times 3 left over, which should be our 6. Okay. The nice thing about this factorization, and this is the fully factored polynomial, I have this monomial that's multiplied by this trinomial. It has 3 terms. But the nice thing about these problems is that you can always check yourself. And I highly recommend that you always check yourself before you wreck yourself. So what do I mean by that? You can check by running through that multiplication again to see if this does in fact multiply to give you the original problem. So if I had 2t times 3x squared plus 4x minus 6, then I can use that FOIL method or distributive property to multiply this guy by each of these terms. And I should get 2 times 3 is 6, so I'm going to have 6x squared t. 2 times 4 is 8, so I should have 8xt. 2 times 6 is, that's going to be a negative 12, since that's a minus sign, and that will be a t there. And since this is in fact the original, then I must be correct here with my factorization. Yet another reason why we covered multiplication before getting into factoring, because you can just multiply out those polynomials to check yourself. So when you've completed a problem and you think, well, I think I've factored this correctly, for the beginning of the semester until you get comfortable with factorizing, go ahead and multiply out whatever you got for your factors. And if you get the same original problem, then you're on the right track. But if you don't get the exact same thing as the original problem, then you've made a mistake somewhere. Okay. Well, I think we probably have enough time for me to factor the second one for you guys. But I'm going to sort of speed through it. Okay, so we had 6a squared minus 18a to the 4th power. I'm going to look at this thing term by term and fully factorize these terms. So if you need to do that factorization off to the side somewhere, you can. 6 is 2 times 3. A squared is a times a, so I have 2 a's there. 18 is 2 times 9, but 9 is 3 times 3, so this is 2 times 3 times 3, and then there's 4 a's here. I'm going to compare to see what are all the factors that I have in common, and it looks like I have 2, 3, and an a here, and I have a 2, 3, and an a here, and that's the, oh, actually I have another a. So 2, 3, AA, 2, 3, AA. That's the most I have in common. So that means that my greatest common factor is 2 times 3 is 6. AA is a squared. So I'm going to write my common factor down first, 6a squared. I'm going to open up some parentheses, and I should have 2 terms in the parentheses since I have 2 terms in the original expression. Okay, but you might notice that if I took the greatest common factor out here from this first term, I took the 2, the 3, and both of the a's, there should be something here. Because I'm not canceling out by subtraction, right? It shouldn't be 0 there. I'm canceling out by division. So if I had this and I divided it by 2, by 3, by a, right? If I divided it by 6a squared, in another word, anything divided by itself is what?
1.
Just 1. And if I took these out, all I have left over here is 3a squared. So this has to be the correct factorization. And to double check yourself, we should be able to take our result, these 2 polynomials, multiply them back together, and see if we get the original problem. So this times 1 is itself, so we'll have 6a squared for our first term. 6a times 3a squared, well, 6 times 3 is going to be 18. And then a squared times a squared should be a to the 4th. So that's the original expression. So that means that this is the correct factorization. Okay, sorry, I ran over a minute here. I'm going to go ahead and stop sharing. If you guys have any questions or need to chat with me here in a second, feel free to hang back, but that is all our time for today. It is Thursday. I see you guys Tuesday and Thursday, so I will see you next week. I'm going to be uploading and updating things in Canvas, so watch Canvas for announcements, watch the Remind app for announcements. And if you have any trouble or difficulties or have any questions at any time, just shoot me a message. Okay, but otherwise, you guys are free to go. I'll see you guys.
Thank you, sir. Have a good rest of your day.
You too.
Bye.
Are we gonna be having like any assignment due this weekend or?
I believe that
I know
there is.
you said
I believe that there is one assignment on factorization, but I don't think that we've completed all the material for it yet, so it's not going to be due this week.
okay, so not to worry about it. That's
Yeah,
just what I was
I'll open
asking.
it up to you guys, and I will send a message out, but I'm not going to make it due this week. So no homework due this week, except for making sure that you've completed all the orientation module.
Yes, sir. Thank you.
But I'll be reaching out to you guys individually if you're missing something.
Okay.
And I have a question on the